for introducing me. Yeah. I would like to say thanks for inviting me to come here to give this talk about to review the uranium thorium dating on some samples for the paleoclimate and anthropology studies. And my name is Chuan-Chou Shen. Yeah, very difficult, I know. Yeah, but easy one here. People call me River because the second character of my Chinese name, right? River, yes. Very easy one. Yes, and I'm a dating guy and working on paleoclimate and some like archaeology cases like here. So, what kind of material you can use for dating? Yeah, the ones corals. Corals very quite good material with the high uranium 3 ppm up to 5 ppm sometimes. Yeah, very easy to be dated by uranium thorium methods. Yes, this one you can date the sample directly by itself because this one is quite good because like Pacific Islands, people use corals as a material for their the compounds. So we can date the corals. So we can figure out the structure age, the construction age of this kind like Venus of the Pacific, the history. Yeah, just published days ago. Yeah, and for the cave stuff, you can date the remains, trace fossils, blah 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 blah, blah a lot. But sometimes the good sample is carbonate again. You can use this one. This is a gel here, a case. This one is Dennis Servan on Tibet. Is a very good study a couple of years ago. And this time have a very thin carbonate crust here on these samples, so we can date the samples directly. Yes. Not the sample directly, carbonate directly. So the carbonate means minimum age of this remain. Yeah. And also you can date for the cave paintings. This cave in Slovenia. Yes, and this one is a cave, and you have a painting inside here. So after painting, the thin layer of carbonate deposited here. This paint, this dye. So we can date things here to get the minimum age of this art. Yeah, of this art. Yes. So using the uranium thorium dating. Uranium thorium dating is uranium-238, decay 234, decay 230. And then eventually led to 206. Yes. To measure this nucleus, scientists like we measure the nucleus using the alpha counter, and then TIMS machine 1980s. We can improve the precision from percent to sub-percent. In 1990s, ITG mass, and then we can improve the precision almost 10 times to the premier level. Yes, very, very exciting. Yes, and then in 2000s, people using multi-corrector ICE mass, and we can down the precision from premier to sub-premier. It's an amazing good precision, actually. For the summary of uranium thorium dating applications in this book, published in 2003, here is a chapter about it. The title is Uranium Series Dating and Human Evolution. This one is some dating method listed in this chapter. The uranium series here. Uranium series means uranium thorium dating. Yeah, here. The datable age from 1,000 to like 300,000, 400,000. This one published in 2003. And then our uranium thorium community tried to improve our technique to push a limit to another labels. So now we can do is push from 1,000 or 100 years to this one to 10 years or even better. Yeah. And this side, the old side from 300,000, 400,000, and then almost touch 600,000 years now. Yes. This is what we could do before. Now I'm going to give you a new technique, what we just developed yesterday, actually. And this technique is quite complicated for radioactive nucleus involved inside. So it's not very easy. It's like C14 dating, you just C14 decays to nitrogen 14, one radioactive C14. And here, 4 radioactive nuclides here. So the equation here is quite complicated. But we can handle that. We can handle that. And besides, the uranium, thorium, different chemistry, different chemical properties. So it's a problem. Yeah. And in my lab, in most of the uranium, thorium dating lab, we just carefully handle the samples and then do chemistry, weight-based chemistry. And then run it on either this a relatively low-price machine or expensive machine, and then we can date them, date the symbols. Yeah. But it's some difficulties here because 238 uranium is the parent. Parents are very big, huge. And then decay to 234. 234 is small, very small. The ratio from 238 to 234 is 10,000 to 1, very small. And 230 even smaller. The ratio between the 230 and 238 atomic ratio, not activity ratio, atomic ratio, is a 10 of minus 10 to 10 of minus 5, very small. So you want to measure the very precise ratio in between. Sometimes it's challenging. Yes, sometimes it's challenging. And besides, this is too big. So when you run it on an ICV system, the tailing from 238 to the low mass domain. So it could cause a bias. It is a problem. And also you run your symbols on the machine, do chemistry on the machine, and then machine you can get ratios, but ratios, not true ratios. You can figure out something like a mass fluctuation, instrumental memory brain interferences, hydrogen dioxide, organic material, and abundance, sensitivity, telling as dictators behavior, and dictators daytime, dark noise, intensive bias, blah 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 blah. You don't care about that. Yeah, we figure out. And also you need a standard spike and then blah 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 blah. So after addressing everything, yes, we can date it. And now some labs, including my lab, we can date the symbols. Like this is corals. Corals is a good material for a paleoclimate study, right? Now we can date this coral. This is one standard called coral M, marine coral. The age is 8.8 years plus minus 0. When you count it, 8.8. Because the bending there, you can count it. And we dated, this is all technique, we dated 9.0 plus minus 0.5 years, not very good. This one is 8.8, I guess, plus minus 3 months. Yeah, so using this one. Leptin, and this is this element 2. Yeah. So we, based on this one and based on the serious studies, like this one, this is counting bendings, how many years? It's 2000, 1900, 1800, 1700, and then this is our age, dated age, and then this almost 1-to-1 ratios. It means we can offer very precise age model for the symbols with the 300 years old corals, no age uncertainty. Amazing good, yeah. Yeah, you probably don't believe it. My students couldn't believe it too. Yeah. They say, oh, River, we can date our samples very precise. I count 6 layers and I got 6 years. 6 layers, 6 years is our routine. Yeah, I told her that. Yes. Now we can do the sample size. We can just need a 0.02 to 0.3. The precision like that, 0.2, 0.5 years, just a couple months. Your sample is good. Sample quality is good. So we can offer like this one, over 400 years records. This one's the age model, almost no uncertainty, almost. Yeah, we should be a little bit conservative. Yeah, almost no uncertainty. So this is some papers we published using the corals. Like this one, volcano eruptions, Pinatubo volcano eruptions in 1996 summer. We dated 1996 summer. Oh no, sorry, it's not summer. It's between the summer and fall, in between. Yes. This one is volcano eruption impact on the mortality of the corals in the South China Sea, done by my student. Okay, most of you care about stegomite. Yeah, here this is stegomite in southern China. You know, this is a tiny bendings in the stegomite, right? Are they annual? The bendings are annual? Maybe not. But in the past decades, people assume the bending here is annual, so they can count the bends and get a chronology. Now we can date it directly on a single layers. The stegomite bendings, the thickness is like that. It's very, very small. And so we dated these symbols given by a Dr. Tan Ming. He gave me. So he said, "Oh, River, I can make your dream come true because this one uranium is high, about 3 to 10 ppm, very, very clean, and we can potentially date it directly on a single layer." He gave me this one after working on about 1 month. I told him, "Dr. Tan, you collected a sample in 2003, right?" And he said, "Yeah, how do you know? I didn't tell you that." I did it. We did it. We cut the surface, and they did the second layer. We got 2002, so the top is 2003. Yeah, I asked him, "You got this sample in 2003?" Yes, 2003. So we got that, and then we did the layers and single layers, and we find the bending. The bending basically annual, about 80%, 90% annual. But sometimes you got a missing layer. Sometimes you have a missing and 4 layers too. Yeah, not always annual, not always an annual. Yes. So once you use the bending counts as your chronology, you should be quite careful. Yes. And here is another example. This we published 2018 using a tiny magnetic signals in this segment. It got a very fast reversal event. It's 98,000. Yeah, 98,000. The reversal. This one's just consider the uncertainty. It's just 100 years. So if you want to solve this one, your dating uncertainty should be very, very precise. So here we 98,000 plus minus 39 year only. Yes, plus minus 43. So we can solve this very fast centennial transition. Yes. And now we use a segment to reconstruct the 80,000 to 15,000. A lot of excursion events here. This one still in preparation. We'll submit soon. We'll submit very soon. And for Paleo-Climate, this guy is Dr. Wang. I guess some of you know that. This is a Hulu Cave, very famous Hulu Cave records. Hulu Cave records get the monsoon records. Follow the summer installation. Also pairs with the green and data 018 climate conditions. Yes. So this one published in 2001, and then after that, lots of, I would say, researchers working on related studies. And then you can also date the bones, different bones. You can date it and then drill it, and date it. But bones, for the fresh samples, the uranium is very low, or only ppb. But for the remains in cave, this one always up to ppm. So it's diffused from outside to the sediment, to the soil, to the bones. So for this one, the best, I would say, for my personal opinion, the best lab in the ANU. Yes. So those uranium thorium could diffuse between in the bones. So you should make a model age, open system models, and get this one age. And this one age is minimum age. Minimum age. So this remains the age. True age is older than the determined age. Yes. This you can and you can drill it to the chemistry, or you can just hit it using laser ablation method, like this one. Using laser and introduce the tiny particles to the machine and run it. And so you don't need to do chemistry, very easy. So this one is very easy, very easy, very fast, 10 minutes, less than 10 minutes actually. And this one is in situ, and the micro domain, tens of micrometer, so tiny, so you can do it very quickly. And without chemistry, sounds very good, right? Yes, but because you introduce a sample from your sample to the machine directly, no any separation of uranium thorium from matrix, so you got the interference. It's like a problem. The disadvantage is low sensitivity errors and the poor performance, and then difficult to find the standards and large errors. But advantage is you can shoot it very tiny micro domain and get the age. If the uranium is high, ppm level, so you can get a relative good age. High, like this one. This one, I just showed you the K pending published in 2021, and then 2024 they get another age. This one's a solution-based chemistry, and this one they use the laser ablation, and then get this is a painting down here. They hit it here. They got a 51K. This so you improve your technology on the same sample. You can publish some papers. Yes, good. So Cape Art back in Indonesia back to 51K. Surprise everyone. So in my lab, we also collaborated with the ETH lab to use the laser ablation, but we introduce a spike to mix the samples together. So because we have a spike, we can measure uranium thorium isotope ratios very not very accurately. Accurate is key. Accurately is a key. So for this technique, we can do. Here the title: Holocene stegmite. Very young. This one just 1,000 years. We can date the samples, stegmite samples, using the laser ablation method. But the one important thing is your samples quality should be good. ppm label uranium and very clean, low thorium. And you can do that. Maybe you can do that. Okay, so you can use a carbonate, date the carbonate. You can date the adhering crust using the solution method. You can use a laser ablation. And then we can date it very young. Very young, even less year samples. Get the age answer in the plus minus couple months. And then further, how about the older part? High chain here. And there was here, Chuan-Chou Shen river here, little people. Yeah, we published a paper in EPSL, presented the new half-life of 230 and 234, so this is great. Yeah, so we try to push the dating limit from 400K to 600K. 600K is eight half-lives of thorium-230. Yeah, 600K. So this one, Chen again, his team published a very currently the very standard records from Huru Sanbao's Asian monsoon records from 0 to 640K. Yes. To reveal, of course, the precessional cycle dominates, and sometimes you can see the validity. Yes. And then, but for the paleoclimate and the archaeology research, sometimes for the 600 to 800K, this is still a gap. Of course, you can use the uranium-late method if the sample quality is good. So we have been trying extend our technique from 600K to another limit. Did we make it? Yeah, we did actually. In 2014, we published all these uranium-thorium ages here, 856, but the error is quite big, plus 110K and then minus 65K. This error is quite big. Yeah, it's big, but this is the oldest age published in the literature from my lab. We try to improve the precision, yeah, in the past years, because this one I just presented. This one is published in 2013. Now it's almost a decade ago. It's a time to push another limit, but it's difficult. I know it's difficult. So this is a technique, better technique, introduce a uranium beam to the system in 2013 technique. And then this duplicate measurement of a standard. So we got the plus minus 0.3 per mil in 2013. Yes. And then we are using this method and also others protocols to run our uranium. For uranium-thorium dating, the key is a uranium-234 to 38 ratio. Difficult, yeah, not thorium-230. If once your sample is very old, 230 thorium-230 beams big. The challenge is 234 to 38 ratio. So we use this one, and then we got, this is the EPSL 2013 variation standards, 0.3 per mil. This is now ours. It's a tiny, this is a variation like that, and then it's a tiny, plus minus 0.08 per mil. Yeah, we push from the sub per mil to sub epsilon level. So it's easy. Oh no, it is very difficult. And then here's the example. The samples, spatial samples from 450 to 700K, and then for grade one, the age determined by channel of 2013, and the purple one with a smaller error bars made by our new technique. Yeah. So here, 700 plus minus from 20K to plus minus 6K. If your sample is good, it means that if samples, for this case, your samples should have a 0.5 ppm uranium or higher, 0.5 ppm uranium. Yeah. So once we push from sub per mil to sub epsilon levels, so we noticed the decay constant should be slightly revised, should be refined. You'll see maybe tomorrow. I don't show the new decay constant here, but you will see very soon. You will see very soon. So now we push the limit from 600K, this is a limit of the technique before, and we push it to 700K, almost, I guess we can touch 800K someday, hopefully someday, yes. So this is all I have, yes, I guess. Oh, so in our lab, we also developed different technique for carbonates, natural carbonates, like major trace elements, magnesium, calcium ratios, or the rare earth elements, like this one. Rare earth elements can reflect the dust storm events, so it's quite good. So now we can do, for this one, carbonates, this one, in the past, students should do drill samples and do a chemistry and run machines 5 samples per week. Now we can do 30 to 50 samples per 1 day. 1 day we dissolve and run. So you want how we can do that? 2011, this paper. So you can do it by yourself in your lab. Yes. So we developed uranium thorium and also other techniques. So we want to. So you can consider my lab for your collaborative partner. Yes, I would say that. And then what else? Oh, this is almost the last one. Thank you for very great reception dinner last night. We got a very good view here. Yes, and also very good music yesterday, and also very good talks yesterday too. Yes. And this here is my last slide. So here I am presenting you our the past and current uranium thorium techniques and some examples in the paleoclimate and anthropology studies and also our new technique. Yeah, and I'm revert here my WeChat. Yes, you can scan if you want to contact with me. Yeah, and oh, I know the European guy wants to use a WhatsApp here. Yeah, so so this is all I gave you today. Okay, thank you very much.